Hi everyone. Today we'll be discussing the LeetCode problem of the day, maximize the minimum powered city. So you're given 0 indexed array stations of length n, where stations of I represent the number of power stations in the ith city. So initially you have n stations, and the value of this ith position is denoting the number of stations in the particular city. So each power station can provide power to every city in a fixed range, which is denoted by R. So that means, suppose we have R equal to 2 and you are at this station. So this station can provide power to the current station and 2 stations to the left and 2 stations to the right. So that's what he's mentioning, such that I minus R is less than equal, I minus J is less than equal to R. So a particular station can provide power to the range R equal to 2 to the left and 2 to the right. So all these cities are powered by the stations of this city. And this is the same for all these cities. And the power of the city is the total number of power stations it is being provided power from. So the stations in this city is providing power to all these cities. And suppose we have this city stations will provide power to all these cities and so on. So power of a particular city is the number of stations it is being powered from. And the government has sanctioned to build K extra power stations, which can be built in any city and can have the same range as the pre-existing one. So you're given two integers R and K, and you have to return the maximum possible minimum power of the city if the additional power stations are built optimally. So also note that you can build K power stations in multiple cities, or you can build it in the same city. So you can build it anywhere. Let's look at the first example. So here we have stations. So in the first city, you have 1 station, second city, 2 stations, then 4, 5, and 0. So this is the stations array. So if you want to calculate the power of each city, here we can see that R equal to 1. So this city stations will power to this station and to this station. So here we don't have any stations, so we ignore that part. So this one is used to power here and also here. And let's see this station. So these two stations will power the cities, will power this city, will power this and this. So these two stations will power all these cities. So I'll just add a +2, +2, and +2 here. Now, if you see this city, since R equal to 1, this city's stations will power all these cities. So add a +4, +4, and then +4 here because of this. And same thing, because of this station 5, it will give power to all these cities. So we'll just add a +5 to all of them. So if I just add all of them, the total power will be, in the first station, first city, we'll have 3 power. In the second city, 7. And the third, 11. And here 9. And here 5. So this is the initial power configuration of the cities. So we can also verify it. So here we have 3, and this 3 we are getting from this and these cities. And this 7 we are getting it from this, and this. So 4 + 2 + 1 is 7, and so on. So this is the stations configuration of all the cities, and this is the power configuration of all the cities. So in the problem, he asks you to return the maximum possible minimum power of the city. So in this initial configuration, the minimum power of the city is 3. So the answer will be 3. So you have to maximize this minimum quantity. So to do that, he's trying to install two more stations at this point. So if you add two more stations in the city 1, so this two stations will power this city, the previous city, and the next city because r equal to 1. So because of that, we'll get a +2 power here, +2 power, and +2 power here. So the updated power of all the cities will be 5, 9, 13, 9, and 5. Now in this array, we can see that the minimum power of all the cities is 5. And this 5 is the maximum possible. So you can't achieve a greater minimum than this 5. So for this input, the answer is 5. So let's quickly look at the second example as well. So here we have stations as follows. Since r equal to 0, suppose this station will only power this city. So the power array will also be the same, which is 4, 4, 4, 4. And here we have k equal to 3. So you can build 3 stations anywhere. So initially in this array, you can see that the minimum value is 4. And you are trying to maximize the minimum value. So if you try to add, since k equal to 3, you can add 3 stations. So if you add one station here, one station here, one station here, then your total power will be 5, 5, 5, and 4. But in this configuration also, we can see that the minimum value is again 4. Or instead of all ones, if you try to add all the stations in the first one only, then it will be something like 7, 4, 4, 4. But in this configuration also, we can see that the minimum value is again 4. So we can't generate a minimum answer greater than 4. So the output remains 4. Now for the constraints, the value of n is 10 power 5 and each station value can be up to 10 power 5. And the radius will be from 0 to n minus 1 and k can be from 0 to 10 power 9. Before going to the approach, I just want to quickly explain a concept of prefix sum, which we will be using in this problem. So let's say we have few boxes. Let me just mark them. 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have 9 boxes, index from 0 to 8. And you are given a query saying that I want to add 4 balls from box number 2 to box number 5. So to do this, initially all the boxes are empty. So I'll just write it as 0. And if I see this query, I just have to add 4 balls from box number 2 to box number 5. So for this, I can just iterate from box number 2 to box number 5 and just add a +4 in each of them. And suppose I get another query saying that I have to add 5 from box number 4 to box number 6. So again, for this, I can iterate from box number 4 to 6 and just add a 5. So this will be 9. This will be 9. And this will be 5. So after 2 queries, this is the resultant array after these operations. And each of the query is taking order of n time, because for each query we are iterating from the range starting to the end and just adding the element. So what if there's another technique that is okay, so this is our final array. Let me just take one more query so that it will be a bit more clear. Maybe add a 3 from range 1
to range 3. So this will make 3. Okay, sorry, I'll write here. This will make 3, and this will be 7. This will be 7. So the resulting array should be something like this: 0, 3, 7, 7, 9, 9, 5, 0, 0. So after adding all these 3 queries, this should be our final output. Now let's see the other way we can add these queries using prefix sums. So first I got a query saying that I have to add 4 from index 2 to index 5. So instead of iterating from index 2 to index 5, I'll only add the 4 at index 2. And at other indexes, I won't add it. So what this does is, so this will be our array 0, 0, 4, 0, 0, 0. So on this array, if we take a prefix sum, so prefix sum in the sense, for the current element, we'll just add the previous element. So prefix of I is a plus, yeah. So for this array, if I take the prefix sum, so this array will become something like this: 0, 0, 4, and this 4 keeps moving forward. So it will be carry forward till the end of the array: 4, 4, 4, 4, 4. So this is the array, and after performing the prefix sum, we will get this array. But we can see that in the first query, we are only meant to add 4 from index 2 to index 5. But in this prefix array, we can see that the 4 is getting added from index 2 till the end of the array. So to counter this, what we can do is, we need 4 only till index 5. So at the next index, which is 6, I will add a -4 in the array. So what this does is, so to this array, when we do the prefix sum, we have 0, 0, 4, and this 4 keeps carry forward, 4, 4, 4. So it keeps carry forward till this index 5, and once we encounter this 4, so these both will get cancelled, and this will be 0, and the rest of the array will become 0. So now what we saw is, instead of iterating from 2 to 5 and adding 4 at each position, we can just add a 4 at index 2 and subtract the 4 at index 5 plus 1, which is the index 6. And after doing that, when we take the prefix sum of this array, we will get the 4 added in our desired range. So the same thing will apply for the other queries as well. Also, we can see that this query is order of 1 operation because we are only adding at this and subtracting at the 5 plus 1. And at the end, we are only performing the prefix array operation once. So let's see what happens when we perform all the operations. Let me just erase this. Yeah, the first operation was add a 4 at 2 and subtract 4 at 6. So this is the array. The second operation, add a 5 at index 4. So at 4, you will add a 5. And you want this 5 to be carry forwarded until 6. So at 7th index, you will add a -5. So that this carry forward of 5 will stop here. And for the last query, you have to add 3 at index 1. So at index 1, I'm adding a 3. And at index 4, we have to subtract a 3. So it was 5 previously. So 5 minus 3 will be 2. So this is the array we found after adding these queries. And once we have this array, just take a prefix sum of this array, like using this formula. So first we have 0. Then 3 plus 0 is 3. 4 plus 3 is 7. 0 plus 7 is 7. 2 plus 7, 9. 0 plus 9 is 9. Minus 4 plus 9 is 5. And minus 5 plus 5 is 0. And 0 plus 0 is 0. So after taking the prefix sum, we can see that this array exactly matches with our output. So with this, what we can say is we can add the queries at the starting point at the and subtract this at the ending point plus 1. And at the end, when we perform the prefix array, we will get the desired output. And there's one thing to note here, that suppose you have a query like this. We just write 0, 1, 4, 5. So you have a query like add a 5, okay, add a 7 from index 2 to index 5. 0, 0, 0, 0, 0. So in this case, what we do is first we add a 7 at index 2 and we subtract a 7 at index 5 plus 1. But here we can see that the sixth index does not exist. So we don't need to subtract a minus 7. So let's say we write a minus 7 here. What happens is when we perform the prefix array of this will be 0, 0, 7, 0, 0, 0, 0, 7, 7, 7, 7, and we stop here because the array is only till index 5. So it doesn't matter if we subtract a minus 7 or not, because we are only iterating till here. So this is the corner case. If the right is equal to the last point, then we don't do the subtraction, because it doesn't matter even if we subtract or not. Yeah, so this is the algorithm we will be using.
Now let's go with the approach. So initially you have the stations configuration, and using that you want to build the power configuration of each city. And to do this, like we discussed, so again, in this example, we have r equal to 1. So station at city 0 will provide power for cities in the range r equal to 1. So from -1 to +1. So since -1 doesn't exist, it powers city in range 0 to 1. And stations in city 1 will power the cities. So this station will power cities in all this range. So I minus r to I plus r. So we can say from 0 to 2. And station 2 we can say from 1 to 3. And for station 3 we can say from 2 to 4. And for station 4 we can say it will power cities from station 3 to station 5, but 5 doesn't exist, so we'll only have till 4. So initially we can just for each station we can iterate on this range and add the current value, but doing that will give us a complexity n into k, which will go out of bound. So like we just discussed the sweep approach, we can use it to fill the values and then use the prefix sum to get this value, get the final answer. So let's quickly do that. So this one we have to add from index 0 to index 1. So at index 0 I'll add a +1, and at index 1 plus 1, which is index 2, I'll add a -1. Then for the next one we have the value 2, and it is getting added from index 0 to index 2. So at index 0 I'll add a +2, so it will become a +3, and at index 2 plus 1, which is at index 3, I'll add a -2. Now for this, at index 1 I'll add a +4. So at index 1 plus 4, and then at index 3 plus 1, which is index 4, I'll add a -4. Now coming to this one, at index 2 I need to add a +5. So at index 2 plus 5, adding a +5 will make this value 4. And at index 5 I need to add a -5. So index 5 is out of bounds, so we don't need to add anything. And this one, 0 should be added at index 3, and 0 should be added subtracted from index 5. So since it's a 0, we don't need to add anything. So this is the array we got, and we just need to take the prefix sum of this array. So it will be 3, then 3 plus 4, 7, 7 plus 4, 11, 11 minus 2, 9, 9 minus 4, 5. So we can see that we have exactly formed the power array just by using the sweep prefix array technique. So once we get the power array, so this is what we need. Let's remove all of the other. Yeah. So currently we have the power array as follows, and in this the minimum value is 3, and in this example we have k equal to 2. So we're trying to maximize the minimum value. So to do this, we can think of using a binary search. So initially we'll take a low value and high value, and low plus high by 2, you'll get a mid value. So this mid value will be the maximum value that can be in this array. So suppose my max value is should be 3. So max is 3. So in this array, you'll iterate and you'll see if all of the values are greater than equal to this 3. So we can see that all of the elements in this array is greater than equal to the number 3. So that means 3 can be my potential answer. So this 3 will store it in our answer. And since 3 is our answer, we will try to move in the upward direction. So we'll try to increase the limit. So we'll try to increase the maximum threshold. So suppose, let's say we want to have the maximum value as 5 in the final array after adding 2 stations. So let's see for 5 what happens. So we have 5. So first we have the station which has the value 3, and 3 is less than 5. So to make 3 reach 5, we need to add 2 more stations. And luckily we have k equal to 2. So we can add 2 more stations at this point, at the city 0, to make this value 5. So this value will become 5. And since you're adding 2 stations here, the next value also will be incremented by plus 2. So this will become 9, 11, 9 and 5. So this will be my updated array. So using 2 stations, you're able to achieve this threshold. So the maximum value, like all the elements in this, is at least equal to 5. So we can say the minimum value of all these array is greater than equal to 5. So 5 is reachable. So the value 5 is achievable. So in our answer, we'll store a 5. And since 5 is achievable, we'll try to we'll try to increase the threshold. So suppose let's increase the threshold, and let's say maybe what if 6 can be my answer. So let's see for 6 what happens. So in at the first city you have the power 3, and you want the power of all the stations to be at least equal to 6. So to achieve this, you need to build at least 3 stations. And since the value of k equal to 2, so you can't build 3 stations. So that means you can never achieve the minimum power equal to 6. So in this case, 6 is not achievable. Since 6 is not achievable, any value greater than 6 is also not achievable. So we try to reduce our threshold. And by doing this binary search, at some point, we will find our answer. So let me take an example and see how we do it. So I'm using this array as the power array, power of each city. So this configuration might not be achievable from the stations, but just for the example, we'll take this. And in this, we have r equal to 2, and k equal to 2. And currently in this array, the minimum value is 1. And we want to try to maximize this minimum value. Now, when doing the binary search, suppose, let's say my mid is 5. Not 5. Let me take mid is 4. So when iterating on the array, first I'll start here. So this 4 is greater than equal to this 4. So it's fine. So next value is 5. So 5 is also greater than equal to the 4. So we don't need to do anything. So now here we have a 2. Now since we want all the values to be at least equal to 4, we'll try to add 2 more stations, which will give this 2 a boost of the power. So to do that, we can add a station at this point. So by doing this, 2 units of power will be added in all this range. So I minus r and I plus r. Here we have r equal to 2. So the value 2 will be added in all these positions. But we can see that all the values in the previous, all the cities in the previous to this current city is already passing the check. So we don't need to add the additional value to it. So what if we move this ahead? So what I mean to say is, instead of adding the extra 2 connections in this city, what if I add it in this city? So by doing this, the plus 2 gets added in the following, in this range. So we can see that by doing this, in this 2, the plus 2 is getting added. So this will become 4. But the advantage of doing this is all the cities to the right of it, plus 2 is getting added. So in future, you can see here we have a 1. So this 1 is also getting an increment, and this is becoming a plus 3. So by this, we can say that whenever we see a particular city wants to have a connection added, we should not add the extra connections in that city. We should add the extra cities in a future city, such that the left value will intersect with the current city, so that we can maximize the answer. So in this example, we will add a city here. So because of that, all the cities in this range will have a plus 2 increment. So this will be 4, this will be 7, 6, 3, and 7. Let's write the entire array. So this is our updated array. And we have added 2 connections to achieve this. So now 2 is satisfied because it is 4 and it is at least 4. Next we will go to this next city and it has a 7. 7 is greater than 4, so we continue. Next it's a 6 and next it's a 3. So now we have a value which is less than 4. So we will try to reach this 4. So to do that, we need to add at least one connection. But we can see that we already used 2 connections and the maximum allowed connections is equal to 2. So that means there is no way for this city to reach the value 4. So that means there's no way we can achieve the maximum value equal to 4. So since we can't achieve a maximum value equal to 4, we can also not achieve a maximum value 5. We can also not achieve a maximum value 6, and so on. So this is where binary search comes in. And so we'll try to reduce our threshold. So we'll try to see reduce our threshold. So maybe we'll check for mid equal to 2, whether this is achievable or not. So let's just quickly see that. So we just now saw that 4 was not achievable. So let's try for 2. and see whether this 2 is achievable. Again, we have r equal to 2, k equal to 2. So now we are looking for 2. That means at least the value should be equal to 2. So in this, it's a 4. So 4 is greater than 2. So we move forward. Next, it's also greater than 2. This also greater, greater, greater. And this is the first city in which you found a value which is less than equal to the, which is less than the maximum threshold you have set. And you just need to add one connection so that this value will reach 2. So to do that, like we discussed, you can add a connection here. But by doing this, you will also do an increment on the previous cities. But we know that the previous cities are already passing the threshold, so there's no need to increase the cities again, or the city's power again. So instead, we can add a city at this point, connection at this point, so that all these cities will get an increment. So if you add a connection here, then the array will be 2, 6, 5, 6, 3. And you used one connection. So 2 is at least equal to 2. So this is satisfied. Then 6 is greater than 2. 5 is greater than 2. 6 is also greater than 2. Also the 3 is greater than 2. So we can see that all the values are at least 2. So the value 2 is achievable. So in our answer, we will store 2 because 2 is the maximum answer we have achieved so far. And since we are able to achieve 2, we'll try to increase the threshold. So now let's say the threshold is 3. Let's try for 3 whether this maximum value is achievable or not. So let's start again. So this 4 is greater than 3, so we continue. Here also we continue. Here also. Here we can see that 2 is less than 3. So to achieve the 3, we need to add one city. And like we discussed, we need to add a connection at I plus R. So we need to add a city here. Sorry, we need to add a connection here. So when we add a connection here, all these cities will get an increment. So the updated power will be 4, 5, 3, 6, 5, 2, 6, 4, 5, and 2. And you have used one connection so far. One connection at this city. So by doing this, here your threshold 3 is met. And then you will proceed. So next you are at 6, then you're at 5. Here you see you're at 2. Again, since you are at 2, you need to add one more connection. And you can see that k equal to 2 and you have only used one connection. So one more connection is allowed. So you will add a connection at I plus R. So you'll add a new connection at this city. So by doing this, you will add a +1 to all these cities. So this will be 3, 7, 5, 6, and 3. Also note that because we are adding a new connection here, this 2 also became a 3. So this 3 is achieved. So we'll move forward. Next we have 7, 5, 6, 3. So all the cities are at least equal to 3. So in our answer, we will store a 3. So 3 is the maximum answer we have achieved so far. And we'll try to increase it further, but we saw that 4 was not possible. So the binary search will stop and 3 is your answer. And here also, while doing the simulation, we will use a sweep array to perform the additions. So like we discussed, when we are iterating, we are at here and we need to add a connection so that this value will become 3. So to do that, initially we'll take a sweep array, which will have all zeros. And when you're at the current position, you need to add a connection at city I plus R. So by doing this, this will power all the cities from the range I to I plus 2R. So this is I. And by adding a connection at this point, it will power all these cities. So I, this is I plus R, and this is I plus 2R. So again, it is same as adding one connection from the range I to I plus 2R. So in the sweep array, at position I, you will add a +1. And at position I plus 2R plus 1, which is at this position, you will subtract a -1. So that means when you do the sweep, this one will get carry forward, and at this point the carry forward stops. And you'll keep repeating this process until you reach the end, and you'll perform the binary search. Now let's code the approach. So the approach might be a bit difficult to understand, so it will be a bit clear when we actually code it. So first let's take the station size. And create a long array to store the power of all the cities. So first let's iterate on the stations. I can use n. So for a particular I, like we discussed, it will power all the cities from range I minus R to I plus R. So leftmost value is I minus R, and rightmost value equal to I plus R. And since I minus R can go negative, we'll use math.max I minus R comma 0. So whenever it's a negative, it will make it 0. And similarly, the right value can exceed the array. So we'll use math.min I plus R comma n minus 1 to keep this values in bound. So this means the stations of I, we need to add it from LA to RI. So we need to add from this to this. So we can iterate from left to right and add the stations, but like we discussed, we can use a sweep array to do it quickly. So in power of LE, I'll just add stations of I. And in power of RI plus 1, I'll subtract stations of I. And also we need to check if this value is less than n, then only we need to subtract it. And once this is done, we just need to iterate the power array and do the compute the prefix sum to calculate the power. So I equal to 1, I less than n, power of I plus equal to power of I minus 1. So by doing this, in the power array, we have computed the power of each city. After that, let's start the binary search. Long, let's take low equal to 0. High equal to, so for the high can be at least equal to the minimum value of this plus the k. So first let's find the minimum value. Long min equal to power of 0. Then let's say min equal to so high can be at least minimum plus k. And also let's take answer equal to 0 and just perform the binary search while low is less than equal to high. So first we'll calculate the mid. So plus I minus mid by 2. Now we'll check if this mid can be our answer or not. So if this mid is possible, then we'll set answer equal to mid. And since the mid is possible and we want to try to maximize the answer, we'll increase the threshold. So low will be equal to mid plus 1. And else case, else in the sense this mid is not achievable, then we want to reduce the threshold. So we'll have high equal to mid minus 1. And at the end, we'll return answer. So all that's left is to fill the possible function. So let's do that. Boolean possible. We will pass the mid value, which is the maximum threshold. So I can just take max for that. We need to also pass the power array and int r, int k. So let's pass our r and k. So first let's just quickly take the size of the array, power dot length. And also let's take an extra array to perform the sweep operations. New LeetCode. Now let's just iterate on the power. So if my current value will be power of I, and if current value is less than this max, then we have a problem. We should try to increase this so that the current value will reach at least max. So if current is less than max, then we need difference equal to max minus current. So we need at least this many number of new connections, new stations to be added. So first let's check if the number of stations I need is greater than k, then there's no way we can achieve this max value. So we'll directly return false. So if this is not true, then we can build this many number of new stations. So from the k, we'll subtract this value because we are using this many number of new stations. And like we discussed, we are at I. We add a new station at I plus r. So new station is added, this many number of stations are added at this point. So because of this, all the cities in the range I to I plus 2r will get an increment. So to do that, in the extra of I, we'll add this difference, and in extra of, let me just calculate the right one. Int right equal to I plus 2 times r, and let me use math.min. So this is the right one. We are using math.min n minus 1 because this term can go out of the array. So to prevent it, we are using this. So extra of ri plus 1, we will subtract the difference. And again, we need to check if this value is less than n. If this is less than n, then only we need to subtract it. So yeah, that's it. So we are adding a new station. So at I, we'll add the difference, and at I plus 2r plus 1, we will subtract the difference. And whenever we get the current power, so current will be power of I plus this extra of I, because in the previous iterations, the extra might get added. So that also we need to carry forward. So previously we have used a separate array to perform the prefix sums, power of I equal to power of I plus power of I minus 1. But here in the same loop only, we should try to do that. So extra of I plus equal to extra of I minus 1. So here only the prefix array is getting computed, and that extra value is getting added to our current power, and this will make our current value. And we will check if that current value is less than max, then we need to add the appropriate difference if that difference is available. And there's a corner case here. When I equal to 0, we don't do this. Like here also we can see that we are starting the loop from 1. So when I equal to 0, we don't need to do this. So just add a check. If I is greater than 0, then only perform this. And once the loop is done and we don't return false at any of the step, so at the end, we'll just return true. Test it. Okay, we have few errors. The current I have not initialized. And this mid equal to low plus high minus low by 2. It's not mid. Okay, it works. Let me submit. Yeah, it works. Finally, let's do the time and space complexity analysis. So for the time complexity, we are initially iterating on the array and just incrementing at left and decrementing at right. So this is order of n. And we are again performing the prefix array of this to perform get the power array, which is also order of n. And here we are running a binary search, which will run in logn time. And in this binary search, we are calling the function possible, and this possible function has a complexity of order of n. So this is n, this is n, and this is NlogN. So total time complexity will be order of NlogN. And coming to the space complexity, I think it will be order of n, because we are just creating two extra arrays. One is power and another is the extra array, which both are of size n. So space complexity will be order of n. I also have the code in Python if anyone wants to view it. I'll add this in the description as well. And let's catch up in the next video.